Good afternoon, calculus students. So Mr. Chen again. So today I would like to talk about the Lagrange error or the Taylor error, the Taylor polynomial error or the remainder error. So this one is for section 8.4, the second half of the notes. So estimating the error of approximation. So we need to know how accurate approximating a function value by using the Taylor polynomial is. So the way to come up with the function is always f of x equals the Taylor polynomial plus the remainder. So we're p sub n of x. So this one is just the Taylor polynomial. And r sub n of x, which is considered either called the maximum error or just a simple error. And also another name for that is called the Lagrange error. Okay, so it's pretty much the same name. So if a function's f is differentiable through order n plus 1 in an interval I containing c, then for each x in I there exists a value z between x and c. So z is right in between the quantity of x and c. So z is the element in between x minus c. So such that the Taylor polynomial, so with the extra term, so r sub n of x. So this one, r sub n of x, is always written as the second order derivative over n plus 1 factorial times x minus c quantity to the power of n plus 1. So don't try to find the exact value of z. So we're looking for the bounds to help us know how large the error that is. So r sub n of x could be, remember z, it's always right between x and c. So find the order polynomial for sine of x center at x equals 0. So that means c equals 0. So started off with the derivative. So for sine of x, so we do know that sine of x, it's an odd function. So it's a roller coaster. So this one is always bounded in between -1 to 1 for the range. So let's find out the interpretation from the derivative. So for the first derivative, so this one is f prime of x, so which is cosine of x. So for cosine of 0, f prime of 0, then that is just 1. And then second derivative, so this one is negative sine of x. So f double prime of 0, which is negative sine of 0, so then that's 0. And then the third derivative, so then that would be negative cosine of x. So third derivative, so negative cosine of 0, which is negative 1. So we're going to use that, the Taylor polynomial, to expand that sine of 0.2 by the approximations of p sub 3 of 0.2. So started off with f of c. So f of c right here. So that, well, using that the Taylor polynomial. So f of c, so sine of 0, that's 0. So started with 0. And then the next term, so derivative f prime of c, so it's 1, times x minus c, so x is 0.2. Again, center is at 0, so 0.2 minus 0, so 0.2. So this one is the third order polynomial, so the next one. So second derivative at c, which is 0, so 0 times 0.2, which is 0. So that means for p sub 3 of 0.2, it's just 0.2. Okay, so now we want to find out that the approximation error for this one. So that means we need to find out the next term. So the remainder of r sub 3 of x. R sub 3 of x. So the remainder r sub 3 of x. This one I should state that it's because you started with 0. N equals, well, n equals 0, n equals 1, n equals 2 right here. So in order to get that, because this one is the third order from the n equals 0, n equals 1, n equals 2, or you can say that the first term, the second term, the third term. So this one I would like to put in, supposed to be r of 2, because you need to get the derivative for the next term. So this one's supposed to be r sub 2 of x, because n equals 2. So which means that it's the third derivative of z over 3 factorial times x minus c. So c is 0 here to the third power. So this one is just like 0.2 quantity to the power of 3 over 3 factorial, because the third derivative, so that would give you -1. So let's say that using c, the value of c as 0, so this one will be -1. So that means the remainder, it would be considered -0.2 quantity to the power of 3 over 6. So you can say that this one would be the maximum error if you take the absolute value of this. So this would be the absolute error. Okay, so now let's see what else that we have for the rest of this. So here's the analysis. So let's check our Taylor polynomial approximation. So a calculator give that sign of 0.2, about 0.196693308. And then for the error that we try to approximate, so the error that we found, it's -0.2 quantity to the power of 3 over 6, the one that we found. So by the time that you subtract, so you get the number which is 0.198666667. So the difference is about 0.000002, which is less than 0.000006. So try to approximate the error here. So the error, which is it's about this number. So 0.2 to the power of 3 over 6. So this one is the maximum error. Okay, so you take the absolute value of that. So you get that positive 0.2 quantity to the power of 3 over 6. So now the next example here. Find the third Taylor polynomial centered at 1. So c equals 1. And for the function is f of x equals natural log of x. So, and estimate the error. Okay, estimate the error. So we need to find out the actual error, not the maximum. Okay, we can compare those two error here. So with p sub 3 of x is used to approximate f of 1.5. So started with the derivative, so f prime of x, which is 1 over x, f double prime of x. So we do have -1 over x squared. So this one is saying that it's the third order polynomial. So started off with f 1.5. So that's it's about, so f of c, so natural log of 1. Okay, so natural log of 1, that is 0. Okay, so the first term is 0. And then the next term, which is f prime of c, so 1 over 1, which is 1, over 1 factorial times x minus c. So x is 1.5 minus 1, then that'll be 0.5. Okay, so let's just show the work. X minus 1, so 1.5 minus 1. To the first power. Okay, so this one is the third order polynomial. So n equals 1, n equals... Okay, so this one is the first term, second term, so the next one. So we need third term of the polynomial. So the next one is f double prime of x, which is -1 over x squared. So at 0 here, well at 1 here, that would be -1. So -1 over 2 factorial. And this one would be considered x minus 1.5 minus 1 quantity squared. So p sub 3 of x. So 3 terms. 1, 2, 3. So for those 3 terms. Okay, so let's find out what that is. So this one is about 1.5 minus 1. So this one, which is 0.5 to the first power, just do 0.5. Minus 1 over 2 factorial. 1 over 2, 1 half. 0.5 quantity square. Okay, so this one is a Taylor polynomial with the third order approximation with the polynomial. So we found the third order Taylor polynomial centered at sc equals 1, and then we want to estimate the error. So the next one, so the error for this one would be so the third polynomial, the third derivative. So derivative of this one, so it's negative x squared, negative x to the power of negative 2. So it's positive 2 x to the power of negative 3. So using that formula, the third derivative is z. We don't know what that is. And then over 3 factorial times x minus c, so 1.5 minus 1, so 0.5 to the power of 3. So in order to maximize the error here, so this number, it's always being bounded to guarantee that's the maximum area, so this number must be 1. Okay, so it's better to have that 1 there, so let's find out. Or to have a maximum quantity, so this one, so it looks like it's going to be, if you plug in c equals 1, so then that would be 2. So 2 over 3 factorial, so 3 times 2 times 1, so that would be 6. And then 0.5 to the third power. So for the maximum error, then that would be 1/3 times 0.5 to the power of 3. And now we want to use the information to find out the actual error for this one. So in order to find out the actual error, so using that, the formula. So the error, not the maximum error, just the normal error. So the actual number, so let's find out what that is. So natural log of 0.5, natural log of 1.5 minus the rest of this, the Taylor polynomial approximation. So this one is subtract 0.5 minus 1/2 0.5 quantity square. So basically just typing that on the calculator. So the error that you'll find out here, it would be less than the maximum error. It would be less than 1/3 0.5 to the third power. Because again, the remainder error, that is the maximum error. Okay, so the actual error that you find out, the actual value of the number, subtract the Taylor polynomial, so, and you'll get that, the actual error. Okay, so thank you for watching the video today. So any questions that you have, feel free to put into the comments. So again, so the last thing I just want to go over once again, so let's ask more questions. So what order P would be accurate? 2000s place. So this one you want to find out, so anything that's less than 0.001, so that means you want to expand the polynomial even further. So we would use that z equals 1, to find out that the derivative, because that, if you plug in 1 for the value of x, it's easier to evaluate the number to get the maximum error. So the next one, you can just find out that the fifth degree, the fifth order derivative, the sixth order derivative, the 7th, the 8th. So it depends on which one that would give you the error. It's bounded less than 0.001. So the higher derivative that you try to take, so you'll find out that it's getting close to that order. So perhaps it might be 7, it might be 8. Okay, so try to figure out what that is. So again, any questions that you have, so feel free to give me the questions from the comment bar, and I try to reply that. Okay, thank you for watching it. So I'll see you guys next time.